Hello, Assalamu alaikum, and we are here in a virtual environment studying thermodynamics. Now, as we know that we have already covered some portion of thermodynamics in the on-campus classes, this is the continuation of the course. Therefore, we are starting from chapter 3 of our textbook. Uh, In this lecture, we will be going to study the different forms of energy, their transformation from one form to another, and first law of thermodynamics. Then we will discuss some work and different perspectives of mechanical work because of rigid boundary motion or expanding boundaries. For instance, in the form of rotating shaft, and the other one expanding boundaries covers the piston cylinder, for instance. The piston moves and the internal confined space expands. The work due to that force is known as work due to expanding boundaries. Then we will discuss different modes of heat transfer, then internal energy, and then we will look into the enthalpy and some practical applications in mechanical engineering or other engineering disciplines. First of all, we should understand what is energy. So, energy is the potential that can produce work. Um, if we look into an example, for instance, we have a ball, a person holding a ball and standing on an elevated height, like third or fourth floor, and the ball, due to its mass, got some potential energy. When he releases this ball, then it travels downward and it gains velocity. Basically, the potential energy is being converted into its kinetic energy, because there is no external source of energy that supplies energy to this ball other than its already stored kinetic energy. So we can imagine that the potential energy is being transformed into the kinetic energy, and the ball is gaining velocity. Um, we can also we should also consider the word of the amount that work that can be produced using certain amount of energy. The potential is somehow a different perspective of it. We can also convert this energy transformation into power transformation. For instance, the rate of change of energy is equal to the rate of energies converting into one form and another. For instance, heat is also a form of energy, and work is also a form of energy. So, in previous lectures, we already discussed the first law of thermodynamics and its mathematical description, and we came to a conclusion that we can write the first law of thermodynamics as energy, sum of all the energies is equal to heat plus work. Here we can see that in this slide, the textbook uses heat minus work rotation. So this is totally up to you. If we consider that any heat input to a mass will raise its energy, internal energy. So we can say that heat transfer to the system that is confined mass, as we are discussing controlled mass approach over here. So any kind of energy that is being transformed to the system will raise its energy, and any form of work that if being done on the system will raise its energy. So we consider heat transfer to the system as positive, and work done on the system as positive. And uh, heat transfer from the system to the surrounding is negative, and work done by the system on the surrounding is negative. So this is all totally up to the user, and we can use sum of all the energies is equal to heat plus work if we uses the convention as I mentioned verbally, whereas in this slide the textbook uses work done on the system as a negative and work done by the system as a positive. So therefore it uses the form of first law of thermodynamics that depicts sum of all the energies is equal to heat minus work. So this is totally up to us, and we will be using sum of all the energies is equal to heat plus work as our first mathematical interpretation of first law of thermodynamics. Then now we can see that this control volume approach as being presented in this slide is somewhat different from control mass approach. In the control mass approach, because there is no new mass coming into the system, because the mass is controlled, that's why we say it's a controlled mass. So for instance, we consider a system that is piston cylinder assembly. If we draw over here that we have a piston, and there is a certain mass of air confined in piston cylinder assembly. So if we consider this is a closed system. No mass can exit this system, and no new mass can enter this system. So this is controlled mass approach. In the previous slide, as you can see, that there is a subscript of CV that represents control volume approach. We are going to discuss it after this CM approach. We can understand that there is no mass entering or leaving the system. Therefore, there is no possibility that a new energy that an entering mass contains will be entering into the system. No, and there will be no energy leaving with the mass itself. For example, if we have a room, and if we open a window over here, if we open the window, then for instance, we are talking about summer, so the hot air now can enter into the room, and when it enters, it will definitely going to carry some energy, and it will be bringing that energy into this room, and there will be some cool air that will be leaving this system. So the system is our room, and then when leaving, the molecules of air will going to carry its energy and taking it out of the room. So incoming air will be adding some energy into the system, or subtracting the energy depending upon its energy level relative to the room, and same will be done by the cool air that will be leaving this room. So the control mass approach is entirely different from control volume approach. Here we have a controlled volume, and the volume is this room, and we can see that until we open the window or doors, and neglecting the minor openings beneath the door and opening in the windows, if we ignore these small openings and we are talking about only the windows and doors for understanding, until we open this room for air exchange between the surrounding, then until then it will be a closed system. There will be no mass of air leaving or entering to the system, and hence we can conclude that this room is a closed system. Now, in the closed system, it is a controlled mass approach, as illustrated in this controlled mass piston cylinder assembly. So the piston cylinder assembly will be same as this room until we open the windows. When we open the windows, now there will be a big difference. Now air will be entering into the system, leaving from the system, and changing the energy of the system with respect to time. And with respect to time, if we discuss for development of understanding, if we open the windows for 10 seconds, and let we assume that we have already maintained the inside temperature around 25 degrees centigrade, and in summer it's 40 degrees centigrade outside. Now if we open the windows for 10 seconds, uh, yes, the hot air will be coming in and making the room environment relatively hotter. But what if we open the windows for a complete minute, 60 seconds? Then obviously room will be getting much hotter as compared to 20-second opening window case. So it means that if we allow mass to transfer across the boundaries of the system, then the energy state of the system is dependent on time as well. Now we can understand it that if we open the window for much larger time, the state of room will be much different if we allow the window to be open for a short period of time. So the rate of energy, if we can depict, now if we consider state 1 as a subscript 1 and state 2 at a subscript 2, and we write it down, the first law of thermodynamics using the subscript, we can see it in the equation being highlighted with red boundaries in this slide, that the energy at state 2 minus energy at state 1 is equal to the amount of heat being transferred into or from the system during this process of getting from state 1 to state 2, plus work done by the system or being done on the system during this process of getting from state 1 to state 2. So we can write it down in this form as being represented in this slide. The heat we can initiate the internal energies with the subscripts. For instance, E2 minus E1 is equal to U2 minus U1. U is the internal energy, as we have already discussed it in the previous lectures. U2 minus U1, because internal energy is the property of this system, whereas heat and work is not the property of this system. Heat is heat can transform, heat can enter or leave into the system, but it is not the property of system. We cannot quantify that this amount of heat is being present in at state 1. So we can write Q1. No, we cannot write Q1 minus Q2. However, we write it as Q1 to 2. Heat transfer to the system or from the system between this process during this process of getting from state 1 to state 2. So we write energies as E2 minus E1, whereas we write work and heat as Q1 to 2 and W1 to 2, because heat and work is not property of the system. We know that there are properties of systems like temperature, pressure, internal energy, volume, enthalpy, entropy. So these are the properties of system, whereas heat is not the property of system. We cannot write Q2 minus Q1 is equal to Q1 to 2. No, this is completely wrong. And similarly for the work, because heat and work is not property of the system. Temperature, pressure, internal energy, and other properties of the systems are well established and well understood properties of the system, whereas the heat and work are not. So we can only represent our heat, our first law of thermodynamics in this form, and then we can write it down into this form. And if we expand it, some that sum of all the energies or difference of energies between state 2 state 1 is equal to the difference of internal energy, difference of kinetic energy, and differences of potential energy. And when we sum it up all these differences, we get to a point there where we can define the differences of energies.